Dr. Sridhar, back to you with another video session on what is voltage regulation and how this voltage regulation of the transformer it will be computed for different applications. These are the points majorly we are going to discuss in today's video session. The voltage regulation can be defined as the percentage of voltage difference between no load and full load voltages of a transformer with respect to the full load voltage. Now here the definition here again voltage regulation could be voltage up or voltage regulation up or voltage regulation down. Now generally this is the voltage regulation down we are going to follow. Voltage regulation is nothing but E2, that E2 is nothing but the no load induced EMF. No load induced EMF in the secondary winding. So initially what happens if there is no load? If there is no load, so what could be the voltage? That voltage is nothing but of course V2 only, but that will V2 is nothing but it will change on slightly, it will be changed with respect to the load. But under no load case, how much of voltage means that voltage is nothing but the secondary winding induced EMF E2, and then full load voltage is nothing but the V2 to the full load voltage into 100%. This is the formula we are going to use to calculate the voltage regulation. So in this one, the voltage regulation, if you could clearly observe E2 minus V2, E2 minus V2 is nothing but what happens, this is the drop is nothing but I2 Z2 only, because why there is a difference between no load induced EMF and full load voltage is taking place because of the drop in the secondary winding. How much of drop in the secondary winding? That value is nothing but the I2 into Z2 to V2, that is the value of the voltage regulation. So let us derive the expression for E2 minus V2. Now in order to derive this particular expression, let us go back to the loading phasor diagrams, or if the transformer under load conditions, and what are the phasor diagrams. So that third quadrant portion if you could take, because only we require secondary induced EMF and the terminal voltage. Now if you could refer the third quadrant portion of our phasor diagrams. Now let us take, for the simplification, let us assume the load is inductive type of load. So there will be a power factor, lagging power factor. So in that cases, now what is the V2 vector and what is the E2 vector? Let us draw all the components, and we know that E2 is equals just voltage performance equation V2 plus I2R2 plus J times of I2 X2. So let us draw the V2 as a reference vector. So this is nothing but the V2 is the reference vector. So with respect to this V2, there will be with an inductive power factor, there will be I2 vector. So this is the I2 vector and this is nothing but the power factor angle. So this phi 2 is nothing but the load power factor. Load power factor. Let us draw a vector I2. Then V2 plus I2R2. So in the direction of I2, let us draw a vector from V2. Then this is nothing but this is in parallel to the I2R2. So the distance, the length of this vector is nothing but it is in the exactly it is equal to I2R2. Then again V2 plus I2R2 plus J times of I2X2. So what happens? You have to rotate the vector by 90 degrees in counterclockwise direction. So let us make a vector. So otherwise if it will be continued like this. So with a 90 degrees, let us rotate this vector in anti-clockwise direction by 90 degrees. So this becomes I2X2. Now if you are adding V2, I2R2 plus J times of I2X2, it becomes E2. So this is the voltage. Here for the simplification, what I am representing is V2 is by OA vector and AB is for I2R2 and sorry, not AB, AE is I2R2, E2, D is nothing but the I2X2. Of course, this I2R2 and I2X2 is nothing but these are the complex quantities. These can be revolved into perpendicular and adjacent quantities like AB and BE for this I2R2, and next one is for ED. This can be resolved into two perpendicular components, that is EF, and next one is the CF. So this vector or else if you are trying here also it will remain same. So DF and EF will be the perpendicular components of I2X2 and AB and BE are the perpendicular components of I2R2. So this is the case. Now finally what happens, voltage regulation is nothing but that is the difference between OD and OA. So that the difference is nothing but this vector and this vector. So A to E and E to D. So these two quantities are inclined and these two quantities are complex quantities. That's why with the compass as a center O, at the center O with a radius of OD, let us draw a vector arc onto the reference vector. So let us assume OD is nothing but some letter we can represent here, some F or H. Let us assume OD is nothing but that is equivalent to the O to H. So here OD and OH is nothing but the same. So if you're, why I am revolving this OD vector onto the reference axis means, now the difference that voltage regulation is nothing but that is the difference between E2 and V2. E2 is nothing but it is inclined with respect to the V2 by delta, and again these two are separated by I2R2. I2R2 is not in the direction of V2, and I2H2 is also not exactly perpendicular or not in the direction. So this is the complex by itself, and this vector is also complex by itself. So getting the differences, vector difference between E2 and V2 is a laborious process. So that's why in order to simplify this, let us revolve this vector, or let us rotate this OD vector with the help of some compass as a center O. Let us draw an arc onto reference axis. Reference axis is nothing but onto OC up to H. So this is the case here. So OD, no more OD. So this OD and OH is nothing but this will be E2. So instead of taking OD, you can directly take OH. This is the one case of simplifying the thing. And again, what I am doing is, so only not exactly we require the exact voltage regulation. If you want to calculate the exact voltage regulation, that vector up to OH you have to take. So OH it will be used for exact voltage regulation. But in this presentation, what I am doing is, instead of taking O to H, only I am taking O to C. O to C for approximate voltage regulation. This is for approximate voltage regulation. This is enough, and almost of all the things are calculated based up to OC only. So that is nothing but for approximate voltage regulation, you can take OC. Just we can ignore C to H. This value we can ignore. So that's why what is the voltage, what is the method we are using, it is not exact. So that's why by using this particular formula, whatever the voltage regulations we are going to calculate, that is not the exact value, but approximately in the 99% of cases it will be matched. And don't say this is the exact value, this is the approximate method only, because we are ignoring this much of portion, that is nothing but the C to H portion we are not adding. But if you want to calculate that exact voltage regulation also, we can calculate it, no matter. So this is the case here. Here from the above diagram, what happens, OC is nothing but, this is from O to C is nothing but our E2 now. So approximately OC is nothing but E2. This is the sum of O to A plus A to B plus B to C. So this is, we can explain like this. So we require O to C up to now. So O to C is nothing but O to A is one segment, A to B is another segment, B to C is another segment. O to A anyhow, this is nothing but the V2 only. But A to B we require. How can we calculate the A to B? Now this A to B is nothing but, we know the diagonal, that is I to R2. What is this angle? This AB makes an angle with AA is nothing but that angle, and this theta is same, because this I2 vector and this I to R2 vector are in the same direction. These two are parallel quantities. So how much of angle this AB will make with respect to AA, that is nothing but the theta 2 only, that is a load power factor. So this is theta 2 angle we know, and this is the diagonal also we know. So AB we can calculate that AB is nothing but I to R2 into cos theta 2. That is the vector. That is the one thing. And second one is B to C. So B to C and E to F both are same. B to C and E to F both are same. So E to F we can calculate, because this angle with respect up to this is 90, and whatever this angle, this line and this line, it means A to E and E to D, it makes 90 degrees, and this angle is nothing but theta 2. So automatically this angle becomes theta 2. So in this particular triangle, this is also a right angle triangle, that is EFD. In this one, we require opposite side. So opposite side and diagonal is I to X2. So I to X2 into sine theta 2 will becomes the EF value, that is also equal to VC value. This is the same thing we are going to take here. So E2 is equal to OC is equal to V2 plus I2R2 cos theta 2 plus I2X2 sin theta 2. So voltage regulation is nothing but, if you are rearranging this particular equation, E2 minus V2 is equal to I2R2 cos theta 2 plus I2X2 sin theta 2. So voltage regulation is E2 minus V2, that is nothing but I2R2 cos theta 2 plus I2X2 sin theta 2 plus V2 divided by V2 into 100%. Voltage regulations are always calculated towards percentage only. It is multiplied with 100% in order to get the percentage value. Now this is for lagging power factor loads. Generally, suppose if it is leading power factor, if it is leading power factor means, now here we are going to get the negative value. This is negative is for, this negative sign is for leading power factor cases. Leading power factor. Now positive is for lagging power factor cases. Lagging power factor. So this is the formula we are going to use for the calculation of voltage regulation. And next thing is, for the leading power factors also, now just now also we have taken, this is nothing but the negative, it is used for the leading power factor. The formula and everything is same, but the phasor diagram it will be slightly more changed. So if you want to calculate the voltage regulation for leading power factor, you will get the negative terminal here, and whereas positive is used for the lagging power factors. And next one is, let us calculate the efficiency. That efficiency, it can be calculated of the transformer by conducting some open circuit test and short circuiting test. And not only this open circuit test and short circuiting test will give us the efficiency, we can also calculate the no load circuit parameters, equivalent circuits, and also the regulation of the transformer. So many parameters you can compute by conducting this simple two experiments, that is open circuit test and short circuiting test. This open circuit test, in this test, the rated voltage it will be applied in the LV side. So for the transformer, as we discussed earlier, the transformer will have two sides, two voltage sides, that is a low voltage side and high voltage side. If you want to conduct open circuit test, high voltage side kept open and apply the rated voltage based on the LV side to the LV side, and record the voltage and the current and the energy, because under no load condition, because this condition is no load condition, this wattmeter gives us the core losses, that is nothing but more exactly constant losses you can get. So in order to get the core losses, let us connect the wattmeter, and voltage, no load voltage anyhow, this will be the rated voltage, and this current is nothing but the I0 current. Let us record the voltmeter, wattmeter and ammeter readings here. And coming to the short circuiting test, here low voltage sides is nothing but just interchange the terminals of the transformer. Low voltage side of the transformer is completely short circuited, and in the high voltage side apply the rated current, not the rated voltage. Here apply the rated current. So this current is nothing but you can calculate as the short circuiting current. Now again this W is nothing but, here it will give the full load copper losses, and this is nothing but the short circuited voltage, VSC, short circuited voltage in the primary side. Let us record these three readings, wattmeter and ammeter and the voltmeter, just to table it. And what is the formulas? Already we know that percentage regulation is I2 R2 naught or R2E, that is the equivalent resistance referred to the primary, cos pi plus or minus I2 X2 is sin pi into 100. So here this plus or minus sign, as we know that plus is used for the lagging power factor and minus is used for the leading power factor. Not only for the secondary parameter, you can also take the equivalent to the secondary in the primary, that is only R1SE cos pi 1, cos pi plus or minus I1 X1E into sin pi. This is about the parameters taken in the secondary primary. This is about the secondary parameter. So these are the two formulas. Just substitute the values. We are going to get it from the short circuiting and open circuit test, and substitute here. You will get the percentage regulation and efficiency, percentage efficiency and the full load. And full load means V2 into I2. That is how much of output power. That output power of the transformer is nothing but the secondary voltage into current into power factor. So output power into, so under full load condition means only that voltage is more or less it is constant. Now I2 will be changed based on the loading condition, how much of percentage of the load we are applying here. So based on this I2 we had to calculate. So I2 into full load into cos pi divided by the Input. Input is nothing but what is the input? Output plus losses. So output plus losses will be the input. So output is V2 I2 cos pi. So plus losses are nothing but some no load losses and full load losses. So W naught is nothing but no load loss, and short circuiting WS is nothing but the copper losses. This is the formula we are going to use to calculate the efficiency at any load. Also, at any load means how much of load, that is 50% of the load means, now that percentage of the load is nothing but the N into kVA rating into cos pi divided by N into kVA rating into cos pi plus, now kVA rating, what do you mean by that kVA rating? kVA is nothing but the kilo. Anyhow, the transformers are little bit larger rating, so that's why K is used, otherwise voltage into current. Here also V2 into I2 is nothing but the voltage into current only. So into 10 power minus 3 if you are taking, this is nothing but the kVA, that's all. So don't confuse with this kVA, what is the kVA rating and VA rating. So this is the VA rating is nothing but into, now in this one whatever the voltage is remain same, only our current rating will be changed based on the load, percentage of the load, your current rating will be changed. So these are the formulas we can use to calculate the efficiency and percentage regulations. I hope you understood the single phase transformer. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.